So this is 19C.2. It's kinematics continued, and it's definitely a little more involved than C.1 was. So let's start off by talking about the relationship of position, velocity, and acceleration. So if you take position, which we'll call S of t, and you differentiate it, you will get velocity. I kind of like the way the book did this. They wrote differentiate here. Pretend that says differentiate. Then if you take velocity and differentiate it, blah, 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 you would get acceleration. So if you go backwards, if you start with acceleration and you want to go back to velocity, you have to integrate once. And then if you're at velocity and you want to find the position function, you have to integrate the velocity to get the position. So that means if you want to find the position function, or one way to find the position is to integrate the velocity. This is really important to realize that. Furthermore, if we want to talk about displacement, displacement is the change in position. So that's so important to know that too. It's the change in the position. So in other words, it would be like position 2 minus position 1, or S of T2 minus S of T1. And the way we can get that is we can actually use the fundamental theorem of calculus part 2. That is exactly the integral of the velocity from T1 to T2. Because if you think about it, when you're finding the integral of velocity, you're getting position, and you're evaluating that from T2 to T1. So I just rewrote what I had over there. So this right here is really important to understand how to find displacement. You're just going to integrate your velocity from time 1 to time 2 to get the displacement of the particle or the object over that time interval. Okay, then also we can talk about total distance traveled, which is different, or it can be different than displacement depending on the object. If the object's going back and forth, like say it went back and forth, it started here and it ended here, would the total distance traveled and this displacement be the same? And the answer is no. The total distance is adding up this distance plus this distance plus this distance. So it's like adding this 1, 2, these 3 distances together. Whereas the total displacement is just the change in position from here to here. So it would just be that distance. That would be the displacement. So if the object's going back and forth, the displacement's going to be different than the change in position. The displacement's going to be different than the total distance. So if you want to find total distance, there are actually a couple of ways to do it. One is what I said in C2 is, let's talk about it really quick. If you have this as your velocity, T1, T2, T3, you would need to set up the integral from T1 to T2 of V, and then you'd have to subtract the integral from T2 to T3 of V. That's if you want to get total distance. And because on the top here, if this is velocity, the object's going to the right. And down here, since the velocity is negative, the particle's going left. So if it's going back and forth, you have to find the distances by breaking that velocity into 2 separate integrals. Or if you have a calculator, if this is a calculator portion, on a calculator portion of an exam, you would not take the time to split them apart like this. You would just go straight away to your calculator, and you would do the integral from t1 to t3 of the absolute value of your velocity. Because the absolute value of velocity is going to take this curve and it's going to flip this part up so that you'll end up getting two positive values there. So it's automatically going to take care of the part that's below and flip it up, and so when you integrate you're going to get a positive value. So that's if you have a calculator at your disposal. There's three ways to do this. So there's this first way here, second way, and then the third way is interesting. It's the way the book does it. And I am going to do it that way, and the reason is, well, on these two examples, because even though I've always used these two methods myself, this first method here can be really tedious, depending on your functions. And it turns out the way the book is going to do this is it's going to be a little easier. So a little less computation. And well, probably the best way to do it is to just go ahead and do the example. If you like lists of how, step by step, you can look on page 486, and they do at the top there in that top box, they write down step by step what you're doing. I'm just going to go ahead, you could write that down on your own. I'm going to go ahead and do the example number 8 right now. And I will do it the way the book does, because it's kind of interesting and it works out pretty nicely. So example 8. A particle moves in a straight line with a velocity function t squared minus 3t plus 2 meters per second. Answer the following without using a calculator. So this has to be totally by hand, and that's what made it tedious. Makes it somewhat tedious, as you'll see. Letter A. How far does p travel in the first 4 seconds of motion? P particle. So if it's how far, that's not displacement, that's total distance. And keep in mind, we have no calculator usage on this one. So you cannot just blindly integrate. And the reason is you don't know if the particle's going left and right in those first 4 seconds. So what you have to do is you have to graph velocity. And this is a parabola, and it's opening up because it's positive. So let's factor it and get our zeros. It's going to be minus 2 and minus 1. So it's going to have zeros at 2 and 1. And the y-intercept is 2 as well. We get that from the equation. So we've got this parabola. It's a very good thing we graphed it, because indeed it's not positive on an entire interval. So 0, 1, 2, 3, 4. Okay. So I'm just going to say the way that I'm in the habit, I'll admit it, the way I'm in the habit of doing this is I would split it up into 3 integrals. 0 to 1, minus from 1 to 2, plus from 2 to 4. And that works beautifully. It's a simple setup. It makes sense. But it's a lot of tedious integrating, and we're going to get a lot of fractions, and it takes a long time, very tedious. But conceptually it makes sense. So I'll just write it down just so you know, in case you don't like this other method, you can always fall back on this one, because it will work. Oops, I forgot my dt. So I'm just going to put this out here just so you know it's a good way to do it if you don't mind a lot of tedious calculation. Okay. The other way to do it is to what you want to do is you want to think about the motion diagram. So from 0 to 1, it's going to the right. So I think this is how that book does it. They just kind of show, okay, it's going to the right at t equals 1. It's here. It starts at t equals 0. And then at t equals 1, and then it's going to go left. And by the way, you can tell how far it goes by the area under the curve. This first triangular area is slightly bigger than the 1 to 2, it looks like to me. So it's probably not going to go back all the way. So at t equals 2, it's somewhere here. And then it's going to turn back around and go to the right quite a bit, because this area from 2 to 4 is quite large. So it's going to go quite a ways out here. It's going to end here at t equals 4. And then what we're going to do is we're going to find the positions at each of these points in time. And if we know the positions, we can get the distance between 0 and 1, and 1 and 2, and 2 and 4. So that's the technique we're going to use. So in order to get the position, so I guess I will write the steps. Number 1, make a, what does the book call that thing? A motion diagram, I think they call it. Oh, they made it a sign diagram. Well, I'm going to call it a motion diagram. They make a sign diagram. I think the motion diagram is just as handy, if not handier. Actually, you know what you should do at the very beginning? Graph velocity. That's the absolute most important thing. Graph the velocity first, then do a motion diagram, which I just did over there. Then find the position function, s of t, so that we get by integrating velocity. And we don't have an initial position, so we're just going to go ahead and integrate velocity. So that's going to be t cubed over 3 minus 3t squared plus 2t. And since we don't have limits, it's going to be plus c. Then, because I already have my motion diagram, I know the key places where I need to find my s's, my positions. So I need to find position 0, position 1 at 1, position at 2, and position at 4. So you're going to find the original, the initial and the final positions, and the position where it changes direction. And then I've got this beautiful function here, so I'm going to plug 0 in, and get c. I'm going to plug 1 in, and I'm going to get 1/3 minus 3 plus 2 plus c. Let's see, negative 3 plus 2 is negative 1, so that's going to be negative 2/3 plus c. Then I'm going to plug 2 in, so 8/3. Dropped my pen. Oh my gosh, my pen just fell apart. Shoot. I managed to break my pen slightly. Hold on here. Okay, it's back together again. 8/3, because I had to lean down here. 2 squared is 4 times 3 is 12. And then 2 times 2 is 4. And I worked this out ahead of time. Where did I write it? That's a really good question. S of 2 is 2/3 plus c. That's faster than me figuring it out again. Oh, S of 1. Did I do that wrong? I have 5/6 here. Just a sec, guys. I'm checking my... Oh, I see what I did. Made a stupid mistake. I can't believe I did that. When I integrated velocity, I forgot to divide by 2. Can't believe I did that. Anyway, I did do it. I did make that mistake. Good thing I already checked my notes. And maybe you guys noticed that too. You probably did. So let's go back and fix this. See, it is a little tedious finding these, but trust me, it's way less tedious than doing it this other way here. Sorry, back to what I was doing. Okay, find my place. So this ends up, I got 5/6 plus c there. And then s of 2, 2/3 plus c. And then plug 4 in. So 4 cubed is 64/3 minus, plug 4 in, squared 16 to 8, negative 24. Plus 8 plus c. And if you crunch the numbers, I got 16/3 plus c. At the end, we'll check this on the calculator to confirm. We want to make sure I didn't make any totally stupid mistakes. All right, now we have to find the total distance. So I'm going to erase this part here because we don't need that anymore. And so I'm going from 0 to 1. So I need to do s of 1 minus s of 0. So 5, 6 plus c minus c. So that means we travel the distance of 5, 6 units, in this case meters, going from 0 to 1. Then I have to do s of 1, which is 5, 6 plus c minus s of 2, which is 2/3 plus c. And the c's are going to cancel, and 5/6 minus 2/3, I guess I could do the math real quick. So it's going to be 15 minus 12 is 3/6, or 3/18, sorry. So 1/6. And I do hope I didn't make any stupid mistakes. I just want to check my math. Sometimes I don't always trust my mental math. 15 minus 12 is 3. Okay, 1/6. That doesn't make sense to me. That must not have dropped down very far in reality. That must be a lot smaller area than this other one right here. I'm just kind of looking at areas. Because, by the way, this would be 5, 6, and this, according to my calculations, is 1/6. I'm looking at how I did it ahead of time, and I don't know. Let's see what happens. And then this one you're going to do 4 minus 2, so s of 4 minus s of 2. So 16/3 plus c minus 2/3 plus c. So I'm finding the change in position from 2 to 4. So really what I'm doing is I'm finding displacements, all these displacements, and I'm going to add them up. So the c's are going to cancel. This, oh, they're already in thirds. 16 minus 2 is 14/3. And now I should be able to add all these up and get the correct answer. 5, 6, oh, plus 1/6, so that's 1. So 1 plus 14/3, so common denominator, and then I'm going to get 17/3. So let's check and see if I did this right. Make sure I didn't make any stupid mistakes. We can go to a blank screen, and because you're finding how far it travels in the first 4 seconds, that's the total distance. So we can do math 9, and what was I going to say? It's going to be the absolute value of the velocity. So on the calculator, total distance is the integral from 0 to 4 of the absolute value of the velocity. Okay, math, num, abs, v is t squared minus 3t plus 2, close, comma, x, comma, 0, comma, 4, enter. That's 5.6667. And then, what did I say the answer was? 17/3. So that would be 17 divided by 3. Oh, hey, 5.6667. So I didn't make any dumb mistakes. I know I should have more confidence. Great. So anyway, that's a pretty cool technique. A little more to think about, but the math isn't too bad. We had to do a bit of fractions, but not too bad. Oh gosh, and we're not even done because we have to do part B. Find the displacement of P after 4 seconds. So what I'm going to do is erase some of this stuff. I do want to keep my my values there. This actually isn't going to be bad since I did all that math ahead of time. So the question is, find, this is part B, find the displacement after 4 seconds. So basically from t equals 0 to t equals 4. The beautiful thing about this is I already have the information I need. So that's s of 4 minus s of 0. So that's 16/3 plus c minus c. Oh my gosh, that's so easy. 16/3 meters. Oh, I forgot to put units on my other answer, didn't I? Well, I erased it. So it's just going to go, that was so simple since we've done all that extra work ahead of time. It moves, it changes position 16/3 of a meter. Anywho, let's move on and let's do, so that was example 8. And then there's another example 9. So we should probably do that one as well. And this is the last example. A particle is initially at the origin, so they're giving us our initial position. Initially at the origin. Moving to the right at, I'm writing fast because these videos get so long if I go too slow. So I'm saving time here when in the writing phase. Of course, I made a mistake. It didn't look right. Stop. It accelerates according to, so a of t is 4 minus 2t centimeters per second squared. Answer the following without using a calculator. So we're doing this one by hand again. And then we could always check it with the calculator. Letter A. Find the velocity function of the particle and sketch its graph. Well, okay. Find v and sketch for 0 to 6. Okay, we're given acceleration. How do we find velocity? We integrate. So v of t is the integral of acceleration. And let's just go ahead and integrate that. So we'll make it we'll leave it as an indefinite integral. Integrate that. That's 4t minus t squared. Make sure I don't make any stupid mistakes there. And plus c. That equals v of t. So it does say it's initially at the origin and it's moving right 5 centimeters per second. So that's the initial velocity, 5 centimeters per second. So what I can do is when time is 0, at t equals 0, the velocity is 5 centimeters per second. So if you plug in 0 for t, I'll just go ahead and do it. So this will be 0 minus 0 plus c equals 5. You'll see that c is 5. And that's always the case. This c is always the initial velocity, v sub naught. So you could actually skip this second step I did from now on, and you can, if you know the initial velocity, you can just plug it in there for c. You don't have to do that second step. So now we have our velocity function. And I think that was the first question, wasn't it? Let me find this again. Oh, sketch the graph. Yep, so we want to sketch this graph from 0 to 6. As you can see, I'm going to run out of room. You know what I'm going to do? I'm going to put it up here because it's going to be important, and because I'm going to be erasing some of the, why does it, you never change? It's going to be important. I'm going to rewrite this as negative t squared plus 4t plus 5. And I am going, that's a 5, and I'm going to need to find the zeros. Now I do know it's opening down. In order to find the zeros, though, I am going to negate everything because I like my t squared to be positive. Just the way I'm used to doing it. And then this is going to be negative 5 and positive 1. And so 5 and negative 1 are my zeros. 2, 3, 4, 5, 6. Even though negative 1 is outside the domain we're interested in, I would still plot it. It'll help you find the picture. You'll look at the graph. 1, 2, 3, 4, 5. We know it's opening down. We know that its y-intercept is positive 5. I'm just doing a rough sketch. I don't really care too much. I'm really more concerned about where it's above and below the x-axis. So that's v. Want to make sure and label that v of t, so you know what you're looking at. Okay, so that is the answer to the first one. Letter B, there are two parts. I am going to rewrite the velocity here so I have it. I'll get rid of all this other stuff. Okay, and I can get rid of a bunch of this stuff. And then I've got my graph, and that's great. Okay, cool. B. For the first 6 seconds of motion, I'm trying to think of the fastest way to write that. Determine the displacement. Okay. Find displacement. Well, that means that's s of 6 minus s of 0. So that means I need to find s, which is the integral of velocity. So s of t is the integral of velocity. And velocity is 4t minus t squared plus 5 d of t. And let's just we'll do it as a indefinite integral again. So that's going to be 4t squared over 2 minus t to the third over 3 plus 5t plus c. And it says it's initially at the origin, so that means the initial position is 0. So that means that c is going to go to 0. So if I clean this up, s of t is 2t squared minus t cubed over 3 plus 5t. And now all you have to do is find s of 6 and s of 0. And we actually know s of 0 is 0 because it starts at 0. So all I really need to know is s of 6. 6 squared is 36. 36 times 2 is 72 minus, oh gosh, I think 6 cubed might be 216, but I want to double check. 6 raised to the third. Yep, it is 216. 216 thirds plus 5 times 6 is 30. 72 plus 30. I know we're not supposed to use calculators. That's 102. I could have done that in my head anyway. Minus 216 thirds. I'll get a 3 and a 3. That's 306 thirds minus 216 thirds. 216 to 300 is 84 plus 6. That's 1090 thirds divided by 3, so that's 30. 30 units. In this case, our units are centimeters. So it's 30 centimeters minus 0 centimeters. The total displacement is 30 centimeters. And that's what I got here. Great, we're doing good. Now, the very last question, find the total distance traveled. So we get to practice through that whole process again that I did on the previous one of finding the total distance traveled. And we'll do it the way of the book because it is actually kind of nice. Okay, I'm going to get rid of all this. So I do want to write down though that s of 6 is 30 because that was here. We need to know that. Oh, I need s. Well, I've got it written down. I do need that s function. So s of 0 is 0. We need to know that. We need to know s of 6, which is 30. And let's write down the position function again, which I erased, but I have written here somewhere. Negative t cubed over 3 plus 2t squared plus 5t. So that's all stuff we need to know. So in order to find the total distance traveled, we need to make another one of those motion diagrams. And we are starting at 0. So it starts at 0 here. And because your velocity is positive, I mean it's above the x-axis, it's going to the right. It's going quite a ways to the right because this is quite a bit of area under here. So it's going to the right, and it's starting at s of 0 is 5. And then at, what was this, 5? S of 5, we need to know. At 5 seconds, it's going to turn around. So we need to find S of 5. Then it's going to turn around and go left a little ways to S of 6, which we don't know what, oh, we do know what that is. That's 30. So that's good news. All we have to do is find S of 5. That's the only time it turns around, and we already know the initial position and the final position. And we have a formula for S of 5, or for S of t. So plug 5 in, that's negative 125 over 3, plus 5 squared is 25, times 2 is 50, and then 5 times 5 is 25. So that's 75 minus 125 thirds. So times by 3, let's see, 75 times 3 is 150 plus 75. I'm trying to do everything by hand because it wants us to do it by hand. So that's 225 thirds minus 125 thirds, which is 100 thirds. Okay, so S of 5 is 100 thirds. I'll erase some of this extra stuff. I'll just write the answer here. 100 thirds. We do want our motion diagram. I do not want to erase that. Let's go to a new color. So to get the total distance, it's going to be, we need to get the distance from 0 to 5. We know that because, well, S of 5 is 100 thirds. So that total distance would be 100 thirds minus 5. Okay, I'll get a common denominator. 100 minus 15 is 85 thirds. So it goes 85 thirds of a centimeter. And then from 5 to 6, it goes 100 thirds minus 30. The change, that's the displacement from 5 to 6. Common denominator. 100 minus 90 is 10. So it's traveling 10 thirds of a centimeter there. So if we want the total, we have to add these up. 85 thirds plus 10 thirds is 95 thirds. And what is that in decimal? Let's see, 3 goes into 9 exactly 3 times. 3 goes into 5 once with 2 thirds left over. Okay, so it should be 31 2/3 centimeters for the total distance. Real quick, before we wrap up, let's check that on our calculator. Math 9, and we're going to do total distance, so that's the absolute value of the velocity. So math num abs. Velocity function will go in here. Where are you? Okay. 4x minus x squared plus 5. Close parenthesis, comma, x, comma. We're going from what? Was it 0 to 6, wasn't it? Yep. 0, comma, 6. Enter. 36 2/3. Oh my gosh. What did I do? I made a mistake. Let me see. Let me make sure I didn't make a mistake on entering it in. 4x minus x squared. Okay. So it's supposed to be 36 2/3. I made a mistake somewhere. Okay, dokes. Let's see if I can find it. I did work this out ahead of time, so I might be able to find my mistake. So from 0 to 5, it should be, 125 thirds. All right. S of 5. I'm just have to look through my notes and see if I can find the mistake. S of 5 is 100 thirds. So this is correct. S of 6 is 30. Oh! I see the problem. It's actually not a math, it's not that bad. It's right here. S of 0 is 5. I had copied that down wrong. That makes me feel better. So I didn't make a mistake in any of this math. Okay, let's fix this a little bit. That's why it's a really good idea to check these on the calculator. So if I'm oh, and I had it written right here, silly me. Oh, I did that. I did do 100 thirds minus 5. 100 minus 15 is 85. 85 thirds. $100 minus 30. Oh no, I'm not seeing the mistake. Did I not divide 95 thirds correctly? Oh, okay, I have to keep looking and see where my mistake is. Sorry about this. This is the last problem, so if you want, you can just stop the video if you already know where the mistake is. I'm going to still try to figure it out, though. 100 thirds. In my notes, I only did 100 thirds plus... Okay, let me see here. Let me look at the problem originally. The total distance traveled from 0 to 6. It did start at 5. Oh! Silly me. Okay, the initial... It is without 5. Now I feel so silly. Okay, this is 0. Because the initial velocity is 5, the initial position is origin. So it starts at 0. So this is my mistake right here. Okay. So that means this, okay. This should be 100 thirds minus 0, which is 100 thirds. So indeed, we are supposed to be at, this is not right. We're adding 100 thirds plus 10 thirds is how we should be doing this, which is 110 thirds, and that should be 36 and 2/3. Let's see. 110 divided by 3. 3 goes in there 3 times. 20, that goes in there 6 times. Good. That's going to be 36 and 2/3. Okay. Sorry about that. Anyway, you can see how you have to be. One little mistake can really throw you off. So, anyway, so that's it.